The life cycles of stars. Embarking on a journey through the endless realms of space and time, we unveil the mystery surrounding stars' birth, evolution, and ultimate fate. Starting from dense gas clouds, the journey unfolds through explosive supernovae and mysterious black holes, each phase revealing a cosmic spectacle. Embark on a journey with us to delve into the complexities of star formation, the magnificent changes of stellar giants, and the cosmic dance of stellar clusters. Together, we will unveil the profound enigmas of the universe and our role in it. Stars started their journey as dense regions of gas and dust known as nebulae. As these nebulae are pulled together by gravity, they shrink and break apart, producing concentrated cores called protostars. Picture this. The protostar gathers more and more mass from its surroundings, causing its temperature and pressure to rise. Eventually, nuclear fusion sparks in its core, signaling the beginning of a star's life. During its lifetime, a star goes through a phase known as the main sequence, transforming hydrogen into helium at its core. As energy is released in light and heat, it helps balance the inward gravitational force, keeping the star stable. Stars have a long journey on the main sequence where their mass influences their characteristics like size, temperature, and brightness. A star ran low on hydrogen fuel in its core. This led to a slowdown in nuclear fusion, resulting in the core contracting and heating up while the outer layers expanded and cooled. When low to medium mass stars such as the Sun reach this stage, they transform into red giants, easily recognizable by their enlarged dimensions and reddish color. Imagine a star growing so massive that it becomes a supergiant, stretching hundreds to thousands of times bigger than our Sun. Deep within red giants and supergiants lies a fascinating process where helium fusion emanates, giving birth to elements like carbon and oxygen. As the process unfolds, more energy is produced, prompting the star's outer layers to expand even more, resulting in a significant swelling of the star's envelope. After the helium-burning phase, a star's destiny is determined by its mass. Picture this. A low to medium mass star reaches the end of their life. They release their outer layers in a rhythmic dance, creating a vibrant shell of ionized gas called a planetary nebula. Over billions of years, the remaining core, known as a white dwarf, slowly cools down. On the other hand, high-mass stars experience a spectacular supernova explosion as they reach the end of their lives. Picture this. A dramatic event unfolds as the core collapses due to its immense gravity, leading to a sudden fusion of heavier elements and the forceful expulsion of stellar material into the vast expanse of space. Supernovae, with their immense power, can briefly overshadow entire galaxies, making them one of the most spectacular events in the universe. The remnants left behind by supernovae are influenced by the star's mass that gave rise to them. When the core collapses, it transforms into a neutron star, a dense object mostly of tightly packed neutrons. Imagine a world where neutron stars, despite being just a few kilometers wide, hold a mass similar to that of the Sun. This leads to powerful gravitational forces, creating fascinating occurrences like pulsars and magnetars. When massive stars reach the end of their life, their core collapse can create a black hole. This black hole exerts such intense gravity that even light cannot break free. In the vast expanse of space-time, black holes emerge as mysterious realms where the fabric of the universe bends to such extremes that they give birth to gravitational singularities, marking the final chapter of a star's journey. Countless stars in the vast universe do not stand alone. Instead, they are part of binary, trinary, or even more intricate multiple star systems. Imagine a scenario where two or more stars dance around a shared center, their movements influenced by the pull of gravity. Stars in multiple systems can have their life cycles affected by their companions, resulting in phenomena like tidal interactions, mass transfer, and mergers. When stars come together, their interactions can significantly affect how they evolve. This can lead to stellar flares, X-ray emissions, and the creation of unique objects such as X-ray binaries and binary pulsars. Some stars habitually change their brightness now and then, all thanks to various factors at play. Imagine pulsating variable stars like Cepheid variables experience rhythmic shifts in brightness due to the regular swelling and shrinking of their outer layers. These stars have been vital in guiding astronomers to measure cosmic distances and grasp the vastness of the universe. There are different kinds of variable stars out there. For instance, there are eclipsing binaries where the light dims occasionally because one star moves in front of the other as viewed from Earth. Then there are cataclysmic variables, which experience sudden bursts of energy when material is pulled onto a compact object in a binary system. Clusters or associations of stars are commonly found within large molecular clouds. These constellations are like a family, born from the same cosmic event and held together by the invisible force of gravity. There are two main types of stellar clusters: open clusters, which are young and have a few hundred to a few thousand stars loosely bound together, and globular clusters, which are older and have tens of thousands to millions of stars densely packed in a spherical shape. Exploring stellar clusters unveils a treasure trove of knowledge about how stars came to be and change over time, along with the intricate dance of stellar relationships within these unique settings. As stars evolve, they shed mass through stellar winds, particularly as they reach the later phases of their life cycle. Once upon a time, streams of charged particles, mainly protons and electrons, flowed from a star's outer atmosphere because of radiation pressure and other processes. The winds are crucial in molding the nearby interstellar medium and enhancing it with heavy elements created inside the star. At a time, powerful stellar winds existed in the realm of massive stars that could shed vast amounts of mass, ultimately shaping the star's future evolution and destiny. Imagine a vast expanse of gas and dust that fills the space between stars and galaxies, the interstellar medium. Once upon a time, new stars came to life in the vastness of space. It all begins at the ISM, where gravitational instabilities work their magic, leading to the collapse and fragmentation of dense regions. This process produces protostellar cores, which eventually blossom into newborn stars. A fascinating phenomenon occurs when dense molecular clouds, where temperatures and densities are just right, the intricate process of star formation. It all begins with the gravitational collapse of gas and dust, setting the stage for the birth of new stars. Delving into the intricate relationship between star formation and the interstellar medium is essential for uncovering the enigmas of galaxy evolution and the birth of planetary systems. When stars change over time, they emit vast amounts of energy into their surroundings through different feedback mechanisms. Massive stars can create quite a spectacle, sometimes resulting in dramatic events like supernovae. When a supernova explodes, it scatters heavy elements created in the star's heart into the surrounding space. This cosmic event can also kickstart the birth of fresh stars by squeezing gas clouds in the vicinity. It is essential to grasp how stellar feedback influences galactic evolution to accurately model star formation dynamics, chemical enrichment, and the control of star formation rates in galaxies. Once stars finish their life cycles, they leave remnants that can transform into different forms based on their original mass. When stars with low to intermediate mass, such as the Sun, reach the end of their lives, they transform into white dwarfs. These are compact remnants of stars sustained by the pressure caused by electron degeneracy. When they reach the end of their life cycle, massive stars go through supernova explosions, and what remains after the explosion can be either a neutron star or a black hole, determined by the star's mass and how the supernova unfolds. Behold these compact objects, showcasing intense physical conditions and holding pivotal parts in cosmic events like pulsars, gamma-ray burst, and gravitational wave occurrences. Exploring the journey of stars in different settings offers a window into the intricate dance of galaxies and the relationship between stars and their environment.